previous videos, we learned how to model continuous outcomes using linear regression and binary outcomes using logistic regression. However, many public health datasets involve counts of events, such as the number of hospitalizations or reported disease cases. For these types of outcomes, we often use Poisson regression, which is specifically designed for modeling count data. In this video, we're going to walk through a real-world public health analysis examining the relationship between alcohol consumption and mortality. Our goal is to understand whether people in different alcohol consumption groups experience different rates of death over time, while accounting for other factors like age and drug use. We begin by loading the Tidyverse and Broom packages. The Tidyverse helps us clean, manipulate, and summarize data efficiently, which is essential in public health research where datasets are often large and messy. The Broom package allows us to convert statistical model outputs into clean, readable tables, making interpretation much easier. Next, we load our dataset and take a first look using str and summary. This step is critical. Before doing any analysis, we need to understand what variables we have, their types, and whether there are missing or unusual values. In public health, poor data understanding can lead to incorrect conclusions, so this step should never be skipped. Let's take a closer look at what our dataset is telling us. We see that our dataset contains 1,658 individuals, each with 7 variables. So, this is a moderately sized cohort study. Large enough to estimate meaningful mortality patterns, each row represents one person being followed over time. The variable death is coded as 0 or 1. 1 means the person died during follow-up, and 0 means they did not. Looking at the summary, the mean is 0.2328. This tells us that about 23% of individuals died during the study period. From a public health perspective, that's a substantial proportion, suggesting this may be a higher risk population or a long follow-up period. The variable agein represents age when individuals entered the study. We can see minimum age about 39 years, maximum age about 68 years, and the average age about 52 years. So this is a middle-aged to older adult population, which is important because mortality risk naturally increases with age. This is why age must be adjusted for in our model. It's a classic confounder. The variable alcohol is coded as 1 or 2. From the summary, the median is 1 and the mean is 1.28. This suggests that most participants are in category 1, which likely represents lower alcohol consumption. So our groups are imbalanced, which is important to keep in mind when interpreting results later. Also, we see that we have 3 time-related variables. Time in, which refers to when the individual entered the study, time out, which is when they exited, and time beath, which is the date of birth, which serves the purpose of calculating age at entry. Right now, these are stored as character variables, not dates. That's a problem for analysis because we cannot calculate time differences correctly until we convert them. The variable drug dot use is also coded as 0 or 1. From the summary, mean is about 0.495. So roughly half the sample reports drug use. This is important because drug use could influence mortality and may confound the relationship between alcohol and death. At this stage, we've learned several important things. About 23% of participants died, giving us enough events to model. The population is middle-aged, making age an important adjustment factor. Most participants are in the lower alcohol group. About half use drugs, which could confound results, and time variables need to be converted before we can calculate person time. Now that we understand the structure and content of the data, we're ready to move on to preparing it for analysis, especially calculating follow-up time, which is critical for Poisson regression. So we convert the date variables into proper date formats. Once again, this is important because our analysis depends on time at risk. We need to know how long each individual was followed in the study. We calculate follow-up time by subtracting the entry date from the exit date and convert it into years. This gives us person time, which is fundamental in epidemiology. Unlike simple proportions, rates account for how long people are observed. We remove any individuals with zero or negative follow-up time. These observations don't make sense in a time-to-event context and could bias our results. Next, we convert variables into meaningful categories. Alcohol consumption is recoded into low and high, and drug use into no and yes. This improves interpretability because results must be understandable not just to statisticians, but also to policymakers and clinicians. We then check the distribution of key variables. This helps us confirm that recoding worked correctly, that categories are balanced, and that there are no obvious data issues. So, what do these distributions tell us? Well, we can see that the alcohol groups are imbalanced with far more low drinkers. Drug use is evenly distributed, making it a strong candidate for adjustment, and the outcome occurs in about 1/4 of the population, giving us enough data to model mortality risk. Next, we will do some descriptive analysis. We begin the analysis by calculating the overall mortality rate. This is the total number of deaths divided by total person time. This gives us a baseline measure of risk in the population. The result is 0.014 deaths per person year. What does this mean? It means that on average, there are about 1.4 deaths per 100 person years of follow-up. In public health terms, this is a rate, not a probability. So it accounts for both the number of deaths and the amount of time people were at risk. This is important because individuals are followed for different lengths of time, and rates allow us to fairly compare across the population. This value gives us a baseline level of mortality in the cohort. We'll use this as a reference point when we compare alcohol groups and interpret results from the Poisson regression. Next, we calculate mortality rates separately for each alcohol group. Before fitting models, we always explore the raw data. Now we're looking at mortality rates broken down by alcohol consumption. For the low alcohol group, 217 deaths, about 20,299 person years. Rate, 10.7 deaths per 1,000 person years. For the high alcohol group, 169 deaths, about 7,087 person years. Rate, 23.8 deaths per 1,000 person years. What does this mean? Well, the mortality rate in the high alcohol group is more than double that of the low alcohol group. This suggests a strong association between higher alcohol consumption and increased mortality. However, these are crude rates, meaning they do not yet adjust for other factors like age or drug use. So while the difference is striking, we cannot yet say that alcohol alone is responsible. There is a clear initial signal that higher alcohol consumption is associated with higher mortality, but we need regression analysis to confirm whether this holds after adjustment. Next, we calculate confidence intervals, which tell us how precise our estimates are, and then create a bar plot of mortality rates with the confidence intervals. This visualization helps communicate findings clearly. The figure shows mortality rates by alcohol consumption group expressed as deaths per 1,000 person years. On the left, we have the low alcohol group with a rate of about 11 deaths per 1,000 person years. On the right, the high alcohol group shows a much higher rate, around 24 deaths per 1,000 person years. The bar for the high alcohol group is substantially taller, more than double the low group. This visually reinforces what we saw in the table. People in the high alcohol group are experiencing much higher mortality rates. Each bar includes error bars, which represent uncertainty around the estimate, typically 95% confidence intervals. The low alcohol group has relatively narrow error bars, suggesting a more precise estimate, while the high alcohol group has wider error bars, reflecting more variability, likely due to having fewer individuals. Even with this uncertainty, the intervals show limited overlap, which suggests the difference between groups is meaningful. From a public health perspective, this plot suggests a strong association between higher alcohol consumption and increased mortality. However, it's important to remember that these are still unadjusted rates. Other factors like age or drug use could be influencing this difference. Now we move to the core analysis, Poisson Regression. This model is used when the outcome is a count, like number of deaths, and we want to model rates, not just probabilities. We include alcohol consumption as our main exposure, age and drug use as confounders. We also include an offset which adjusts for person time. This is essential. It ensures we are modeling rates per unit time, not just raw counts. So let's walk through our results step by step. We're looking at a Poisson regression model predicting death rates with alcohol use, age at entry, and drug use as predictors. The model also accounts for different follow-up times using an offset, which means we're really modeling a rate, deaths per unit of time, rather than just counts. Starting with the intercept, the estimate is about minus 9.97, and it's highly significant. On its own, this represents the baseline log death rate when all predictors are at their reference levels. So people with low alcohol use, no drug use, and age equal to 0. That's not directly meaningful in practice, but it gives us a baseline from which the other effects shift. Now let's look at alcohol. The coefficient for high alcohol use is about 0.365, and it's statistically significant with a p-value well below 0.001. Because this is a Poisson model with a log link, we interpret this in terms of rate ratios. If we exponentiate 0.365, we get roughly 1.44. That means individuals with high alcohol use have about a 44% higher death rate compared to those with low alcohol use, holding other variables constant. Next, age at entry. The coefficient is about 0.104, and it's also highly significant. Exponentiating that gives us approximately 1.11. So for each 1 unit increase in age, likely 1 year, the death rate increases by about 11%. That's a strong and consistent effect. Now, drug use, the coefficient for drug use is very small, about 0.023, and the p-value is 0.82. That's nowhere near statistically significant. So based on this model, there's no evidence that drug use is associated with a change in death rate once alcohol use and age are accounted for. Looking at model fit, the null deviance is 1,592.5, and the residual deviance drops to 1,379.5. That tells us the predictors collectively improve the model compared to having no predictors, though there's still unexplained variability. The AIC is 2,159.5. which is mainly useful for comparing this model to others. And finally, the dispersion parameter is 1, which is what we expect under a standard Poisson model. So there's no immediate indication of overdispersion from this summary alone. So to sum up, higher alcohol use and older age are both clearly associated with increased death rates, while drug use does not appear to have a meaningful effect in this model. We then convert model coefficients into incidence rate ratios, or IRRs. These are easier to interpret. An IRR greater than 1 means higher mortality rate, and less than 1 means lower rate. For example, an IRR of 1.5 would mean a 50% higher mortality rate. This is the kind of measure commonly reported in epidemiological studies. All right, now we're looking at the same model results, but expressed as incidence rate ratios, or IRRs, which makes interpretation much more intuitive. Starting with the intercept, the IRR is an extremely small number, about 0.000047, with a tight confidence interval. Just like before, this reflects the baseline death rate when all predictors are at their reference values. It's not something we usually interpret substantively, but it anchors the model. Now, alcohol use. The IRR for high alcohol consumption is 1.44, with a confidence interval from 1.16 to 1.78, and a p-value well below 0.001. This tells us that individuals with high alcohol use have a 44% higher rate of death compared to those with low alcohol use. The confidence interval does not include one, which reinforces that this is a statistically significant and meaningful effect. Next, age at entry. The IRR is 1.11 with a very tight confidence interval from 1.09 to 1.13, and again, a highly significant p-value. This means that for each additional year of age, the death rate increases by about 11%. This is a strong, consistent effect with high precision. Finally, drug use. The IRR is 1.02 with a confidence interval ranging from 0.84 to 1.25 and a non-significant p-value of 0.82. Since the confidence interval includes 1 and the estimate is very close to 1, this indicates no meaningful association between drug use and death rate in this model. So overall, expressing the results as IRRs confirms what we saw before. High alcohol use and increasing age are both associated with higher mortality rates, while drug use shows no evidence of an effect. Next, we check for over-dispersion. Poisson models assume that the mean equals the variance, but in real-world public health data, variability is often higher. If over-dispersion is present, our standard errors may be underestimated, leading to overly confident conclusions. Now we're looking at the dispersion statistic, which helps us check whether the Poisson model is appropriate for these data. The calculated dispersion value is about 2.18. In a standard Poisson model, we expect this value to be close to 1 because the model assumes that the mean and variance of the outcome are equal. Here, though, the dispersion is clearly larger than 1, more than double, in fact. This indicates over-dispersion, meaning that the variability in the data is higher than what the Poisson model expects. Why does that matter? Because over-dispersion can lead to underestimated standard errors. And when standard errors are too small, it can make predictors look more statistically significant than they actually are, increasing the risk of false positives. So while our earlier results showed strong effects for alcohol and age, this dispersion value suggests we should be cautious. The model may be too optimistic about the precision of those estimates. To address this, we fit a quasi-Poisson model. This adjusts the standard errors without changing the estimated effects. It's a practical and commonly used solution in epidemiology. Now we're looking at the quasi-Poisson version of the model, which was fitted specifically to deal with the over-dispersion we just identified. The structure of the model is exactly the same as before, same predictors, same offset, but the key difference is that the quasi-Poisson approach adjusts the standard errors to account for the extra variability in the data. Starting with the intercept, the estimate is unchanged at about minus 9.97, but notice that the standard error is now larger, around 0.70 instead of 0.48. That's the over-dispersion correction in action. It's still highly significant, but again, the intercept itself isn't of primary substantive interest. Now, alcohol use, the coefficient remains 0.365, exactly the same as in the Poisson model, but the standard error has increased from about 0.11 to 0.16. As a result, the test statistic drops and the p-value rises to about 0.023. So alcohol is still statistically significant, but the evidence is weaker than before. This is a really important shift. Once we account for over-dispersion, we're less confident about the strength of this effect. If we translate that coefficient into an incidence rate ratio, it's still about 1.44, meaning a 44% higher death rate for high alcohol users, but now with more uncertainty around that estimate. Next, age at entry. Again, the coefficient is unchanged at about 0.104, but the standard error increases. Even so, the effect remains highly significant with a very small p-value. So age continues to be a strong and robust predictor of mortality, even after correcting for overdispersion. Finally, drug use. The coefficient is still very close to zero, and with the larger standard error, it remains clearly non-significant. There's still no evidence of an association with death rate. Looking at the dispersion parameter, it's about 2.18, exactly what we estimated earlier. And now it's explicitly incorporated into the model. That's why the standard errors are larger and the inference is more reliable. One other thing to note, the AIC is not reported for quasi-Poisson models, so we can't use it for model comparison in the usual way. So, to sum up, the main conclusions stay the same. Alcohol and age are associated with higher mortality, drug use is not. But after properly accounting for overdispersion, the evidence for alcohol is more modest while age remains a very strong and consistent predictor. We then examine diagnostic plots. These help us check whether the model fits well, there are unusual observations, and assumptions are reasonably satisfied. This step ensures our findings are reliable. Starting with the top left, the residuals versus fitted plot. Here, we're looking for a random scatter of points around 0, which would indicate a good fit. Instead, we see a clear pattern. The residuals are larger and more spread out at lower fitted values, then compress as fitted values increase. The red smoothing line also shows a downward curve rather than staying flat. This suggests that the model is not fully capturing the structure of the data, and it's another signal of overdispersion or possible model misspecification. Now, the top right, the QQ plot of residuals. This compares the distribution of residuals to what we'd expect under the model. Ideally, the points should fall along the diagonal line. Here we see a noticeable deviation, especially in the upper tail where points curve above the line. That indicates that the model is underestimating extreme values. In other words, there are more large residuals than expected. Again, this is consistent with overdispersion and heavier tails than the Poisson assumption allows. Moving to the bottom left, the scale location plot. This shows the square root of standardized residuals against fitted values, and it's used to assess whether the variance is constant. What we want is a flat horizontal trend. Instead, we see a clear downward trend. Higher variability at lower fitted values, decreasing as fitted values increase. This confirms heteroscedasticity, meaning the variance is not constant, which violates another assumption of the Poisson model. Finally, the bottom right, the residuals versus leverage plot. This helps identify influential observations. Most points are clustered at very low leverage, which is typical. There are a few points with slightly higher leverage and larger residuals, but none appear to cross the Cook's distance thresholds in a dramatic way. So while there may be some mildly influential observations, there's no strong evidence that a few extreme points are driving the model results. Putting it all together, these diagnostics reinforce what we saw earlier. The Poisson model is struggling with overdispersion and non-constant variance. The residual patterns are not random. The distribution has heavier tails than expected, and variability changes across fitted values. So the big takeaway is that the basic Poisson assumptions don't fully hold here. And that supports the decision to move to a quasi-Poisson or negative binomial model for more reliable inference. Finally, we calculate predicted mortality rates for typical individuals. For example, we compare someone in the low versus high alcohol group, holding other variables constant. This translates statistical results into something more tangible and actionable. Now we're looking at predicted death rates from the model, which helps translate all those coefficients into something more concrete. Here we've created a simple comparison. Two individuals who are identical in every way except for alcohol use. Both are set at the average age, about 52 years old. Neither uses drugs and each has 1 year of follow-up time. So this is a clean, controlled comparison of alcohol's effect. For the individual with low alcohol use, the model predicts a death rate of about 0.0102 per year. For the individual with high alcohol use, the predicted rate increases to about 0.0146 per year. So what does that mean in practical terms? The difference between these two is about 0.0045 deaths per year. That might look small in absolute terms, but remember, these are rates. When we compare them proportionally, the high alcohol group has about a 44% higher death rate than the low alcohol group. That aligns perfectly with what we saw earlier in the model coefficients and IRRs. What this step does is make the result more tangible. Instead of talking about log coefficients or ratios, we're now seeing the actual predicted risk over a year. So the key takeaway here is that holding age and drug use constant, high alcohol consumption meaningfully increases the predicted annual death rate, and the size of that increase is consistent with the earlier findings from the model. And with this, we have reached the end of the analysis. We started with raw cohort data and transformed it into a meaningful public health analysis. We calculated person time, estimated mortality rates, built a Poisson Regression model, and interpreted results using incidence rate ratios. This workflow reflects real-world epidemiological practice and provides a foundation for analyzing many types of health outcomes. In the next video, we will explore data visualization techniques specifically designed for epidemiology, including epidemic curves and prevalence plots.